Hi Rockridge, this is Mrs. Berger, and today we're going to start the Unit 3 on functions. Today we're going to talk about the characteristics of functions, and so it's a lot of visual assessment of functions and graphs. Some of it will be review from Algebra 1, so hopefully some of this is familiar, and then we'll add some new concepts as well. Now, I'm not going to go through the entire warm-up that we had set up for today. I think most folks are comfortable with graphing this line, this y equals 1/2 x plus 1, y equals mx plus b. If you need to, go ahead and take a look at the key for that, but hopefully you feel pretty comfortable with that. There were some students that were having a hard time remembering how this on the warm-up worked, so let me just go through part A for you. When you've got functions that are defined like this algebraically, f of x equals negative x squared minus 2x plus 5. This function f, think of it as a machine, okay? So think of this as a machine. You input things into the machine, your x is your input, and then the way this function works is you'll do these things to that input and then something will spit out as your output. So we read 2a as f of 2. Put 2 into the f machine and see what pops out. So input 2 every time you see an x and go calculate what the output is. So if I input 2 into the f function, what that means is negative input 2 squared minus 2 times 2 plus 5. Now remember PEMDAS, we want to make sure that we take exponents first before we multiply this little imaginary little -1, this invisible -1, okay? So what we'll do is we'll say 2 squared, using the exponent, times -1, so -4, minus 2 times 2, which is 4, plus 5. So -4 is -8, plus 5 is -3, okay? So the output, when we input 2 into the f function, we will output a -3. So I would encourage you to try to input -2 in for x, input 0 in for x, and find out what the f machine pumps out as an output, and go ahead and check that against the key, okay? So I'm going to start today's new material. Once again, some of this should be repeat for you. So, a lot of you saw this in Algebra 1. When we talk about a relation, we're talking about any set of ordered pairs. And remember what an ordered pair is. That's the thing that looks like this, right? X comma y. So any set of ordered pairs. So maybe you have a 2 comma 1, a 3 comma 6, a -1 comma 2, and a 3 comma 4. This is a relation. This is a set of ordered pairs, any set of ordered pairs. A function is a special kind of relation. It's a relation in which no two x values repeat or are the same, okay? So a function is a special kind of relation in which x values don't repeat. If I look at this relation, I have 2 comma 1, so I have x value of 2, x value of 3, x value of -1. Oh, I have x value of 3 again. So this whole relation here is not a function because the x values repeat. Domain, most of you remember this from Algebra 1. Domain, that's x values. Range, oops, can't spell anymore, sorry about that. X values. Range is y values. I also want you to start thinking of domain as input into those function machines, okay? So x values or input, that's domain. And I want you to think of range as not only y values, but also output. So output from those function machines, that's the range. Linear notation, that's just y equals, the stuff that you've seen in past courses. Linear notation starts with y equals. Function notation is when it looks like this. F of x equals something. G of x equals something. Maybe in science class, when you threw a ball, you stated that function as the height as a function of time, okay? So this is function notation. We're saying we input time into the function to figure out what the output height is, okay? So for predicting the future. Representing relations, again, a relation is a set of ordered pairs. We've got several different ways to represent these. On the quiz, you'll need to be able to do all of these. Most of you are very familiar with ordered pairs, x comma y. Most of you are fairly familiar with table of values. You just put all the x's in one column and all the y's in another column and make sure that they match up as they did in the ordered pairs. Most of you feel very comfortable with the graph of a set of ordered pairs. You're simply putting dots on the coordinate plane that respect to these ordered pairs. But not everybody saw the mapping diagrams in earlier courses, so I'll take a second to talk about the mapping diagram. In a mapping diagram, you take all the x values, all of the inputs, and you put them in one bubble. And you take all the y values and you put all the outputs into another bubble. No repeating in a bubble, okay? So even if your x values repeated in your set of ordered pairs, you do not repeat them in the bubbles for a mapping diagram, okay? So that's why -2 only shows up once here. The way you show that it happened twice is using these arrows. An input of -2 had an output of -2 for this guy right here. And an input of -2 also had an output of +2 to take care of that ordered pair right there, and so on and so forth for the other two values. So this mapping diagram consists of a bubble for input, a bubble for output, no repeats, and then an arrow that comes from the input to the output. On the quizzes, I take off if I don't see arrows going in the right direction, if I see repeats in the bubbles, okay? And of course, if they don't match up with what our original ordered pairs were. So knowing that this is what a mapping diagram does and how it works, let's take a look at this example here, example A, and take a look and see if we have a function. Do we have a function, yes or no? And again, to define a function, we have no x values repeating. So let's check to see if any x values repeat. We have -2 causing this, -1 causing this, 3 causing this, and 6 causing this. So no inputs caused more than one output. So we're good here. Yes, we have a function. Yes, it's a function. No x values repeat. And one thing to help solidify this concept of function that I tell my students is, let's pretend like I am a cell phone salesperson at Verizon, and I'm told by my boss that if I sell one cell phone, I'll get, or let's use this example, if I sell 6 cell phones this month, I'll get paid $4. But then the next day, my boss tells me if I sell 6 cell phones, I'll get paid $3. You say, wait a second. You can't tell me that if I sell 6 cell phones, I get paid both $4 and $3. You got to pick one. Okay, that's not a function. That's not a predictable function. If I have an input, I can't predict what the output is. Okay, so if this 6 went to another place, I would not have a function there. Okay, if that real life example helps solidify the concept for you. So understanding that, let's look at part B and see if this one's a function. Are there any inputs that cause 2 different outputs and ruin our predictability? The answer is yeah, right there. We have this 2 causing 2 different outputs. That's a no-no. So no, this is not a function. If you would like on your quiz or test to use this verbiage, no x values repeat, or if you want to say x value of 2 repeats, I would take that as an explanation. If you wanted to say one input causes more than one output, I would take that as an explanation. Anything along those lines is a perfectly good explanation or justification for why you said no, this is not a function. All right, let's practice a little bit here. I want to show you the notation that we use to declare domains and ranges for relations. Hopefully you saw this in Algebra 1. When you state a domain, and we're talking about this table here for the relation, when you state a domain, you say the domain, capital D, is curly bracket, we're going to use set notation, x such that x equals -1, 2, 5, and 6. Okay? The domain of this relation here are all the x values. I have a -1, a 2, a 5, and a 6 to encompass all these x values. So this domain, this relation only exists at these little x value points, nowhere else. The range, on the other hand, capital R, these are y values, so y such that y equals -2, 2, and 3, end curly bracket. That is the set of values in the range of this relation. Only those values are where this exists. For a mapping diagram, I would list my values in one bubble for my inputs and put that in a bubble. And then I would have a bubble for the output values, -2, 2, and 3. I usually put my values and then draw a bubble around because I always make my bubbles too small. And then I'm going to indicate how these relate to each other. Okay, I would map them. I would map the inputs to the outputs. So an input of -1, according to the chart, has an output of 2, 3, and -2. Right? An input of 2 has an output of 3. An input of 5 has an output of 3. And an input of 6 has an output of 2. So that would be my mapping diagram for this relation. So that's another representation of that relation. Now, is the relation a function, yes or no? Well, what did we notice? We noticed that this -1 had 3 different outputs. Very unpredictable. What's going to happen if I input -1? 3 different things happening. So definitely no, not a function. You could justify this by saying the -1, the value of the x value of -1 happens more than once. That would be fine. You can say input of -1 has more than one output. Any of those types of justifications for your answer would be acceptable in a quiz or test. Now, one more way we want to illustrate this relation is by plotting it on a grid. So let's plot this on this grid here. And again, you'll just have, sorry about that. You'll just have the points plotted on the grid. So you'll put a point for each coordinate. So 1, 2, 1, 2, 3, that's your first one. 5, 3, that's your second one. -1, 2, -1, 3, 6, 2, and -1, -2. Please do not connect these dots. This relation does not exist anywhere except these individual points. It does not exist in between or in between. It only exists at these points. So do not connect these dots. This domain only exists at these individual x values. The range only exists at these individual y values. Go ahead and pause the video and take a look at this example here, this example. Pause the video, try it for yourself, and then when you restart it, you'll see the answers so you can check your work. Okay, go ahead and check your work here against the key. If there's any trouble with the answers to A, B, or C, go ahead and check with your teacher when you see them next. Let's take a look at interval notation versus set notation. From now on, when we have a continuous function, so we've been looking at those discrete functions that are just a set of points. Most of Algebra 2 will be looking at continuous functions where things go up and down and we don't pick up our pencil at any point, and these functions live for all this time instead of individual set points. We're usually looking at continuous functions. And there's just no way to declare domains and ranges with little commas in between every value, right? There's just no way that you could talk to me about this and say, the domain of this is, well, gosh, it's -4 and -4.3 and -4.2 and -4.1 and -4. There's just no way that you could make an entire list of every single element of this domain. So we're going to need to use intervals of descriptors. So we're going to use interval descriptors to talk about all the x values that live on here and all the y values that live on here. And it's very, very useful and takes up less space on a piece of paper to do interval notation instead of set notation. If you're trying to declare that a particular function has a domain of every value greater than 2, a shorter way to do this is saying interval notation. The interval of 2 to infinity is the domain of whatever relation we're talking about, whatever function we're talking about. So this inequality, x greater than 2, is displayed in interval notation with 2, infinity. 2 to infinity. Everything in between. 2.1, 2.2, 2.3, 2.4, 2. All of those things that we couldn't possibly list out are displayed here in the interval of 2 to infinity. If you jump down 2 blocks, let's talk about what happens when it's greater than and equal to 2. If that's the case, we put a hard bracket on the 2 to indicate that it's not only everything above 2, it's also including the 2 as well. Okay? So if you have soft brackets, you're saying to the person that it does not include the number. It goes up to the number but doesn't include it. If you're showing hard brackets, you're saying to the person it does include the number, all the way up to and including that 2. Okay? Infinity special, it always gets a soft bracket. Now, if we pop back up to the second line, everything less than 2, you're saying everything in the domain is everything from negative infinity all the way up to 2. When you say x is less than 2, it's negative infinity all the way up to 2 is the domain that you're declaring. Similarly, if you're up to and including 2, you would say negative infinity up to 2, including the 2. All the numbers in between negative infinity and 2 are what we're talking about. Now, if it's in between 2 particular numbers, if you're declaring that this thing only exists between 2 places, you start your interval at the beginning, -5. You end your interval at the end, 3. And you say the interval that we're talking about is everything between -5 and 3. And of course, since neither of these have inclusions, we have soft brackets. Similarly, if you are up to and including, same thing. We start at -5 and we include the -5 all the way up to the 3, including the 3. Go ahead and pause the video and try this chart. Try putting that in interval notation, just like we did on the left, and then come back and check your answers. Okay, hopefully you have these answers here. If not, pause the video and take a look at your work and see where you went wrong. This is pretty foundational. We are going to use interval notation pretty much for the rest of the year, so start to get really, really comfortable with how these work. Okay. The last little note that we want to make on this page is when we are talking about a function like the blue one that I drew here originally that goes on forever to the left and forever to the right, we're going to start that. We're going to say that basically this thing lives for every single x value that we know about, all real numbers. Okay. In set notation, we had a fancy R to show that, all real numbers. So if you're in the curly bracket world of set notation, we had that fancy R to say all real numbers, everything in the whole wide world that we know about. For interval notation, we're going to say from -infinity to infinity. This thing lives left to right, -infinity to infinity. That's interval notation for all real numbers. Okay? So let's start talking about functions that live over these intervals. So instead of individual points like we had at the beginning of the lesson, we've got continuous functions where we don't pick up our pencil, and we couldn't possibly list out every single element of this domain with commas separating them. These are intervals. So with domain, oh, my apologies, where did I find that? Sorry about that. So for domain, I want you to think, what's going on left to right? I want you to make a list of all the x values and list them left to right. Think a horizontal scan, okay? And for range, I want you to think bottom to top, okay? That's a vertical scan. Okay, so when you're talking about domain, I want you to talk to me left to right. Do not go backwards. I want you to talk to me about domain starting at the left and ending at the right. And when you talk to me about range, I want you to think bottom to top, littlest to biggest. Typically, students don't have a hard time telling me things left to right, because that's how we read, newspapers in the United States. Range is a little bit more difficult because obviously when we read a page, we read top to bottom, and that's a little bit backwards. So that's the one thing that we need to make sure that you keep consistent with. List me my range, bottom to top, smallest to biggest. Zeros, we're going to think x-intercepts. If anybody asks you for zeros, you're going to list me where does the graph cross the x-axis. Okay, those are zeros. So let's use our newfound skills of interval notation to declare these domains. And remember, domain is left to right. I apologize, these don't line up perfectly, but let's pretend like they do. Domain of this circle, all the x values that live on this circle are between -2 and 6. Everything between -2 and 6 is the domain of this circle. Range, and again I apologize, let's just pretend like this stopped here and stopped here. The range of this, again, littlest to biggest, smallest to biggest, the range of this is from -2 up to 6 and everything in between. The y values that live on this circle is everything from -2 to 6, everything in between that I couldn't possibly list. For B, the domain of this, now take a look, we've got arrows going on here. These arrows indicate that we just couldn't possibly have enough graph paper to encompass this function. This arrow means if I had enough graph paper, it would go on forever and ever and ever in that direction, to the right and up. And this arrow means it will go forever and ever down and to the left. So if that's the case, my domain, if I was all the way to go to the far, far left-hand side, my domain would start at -infinity. All the x values start at -infinity. And these x values, I have every single x value all the way up to +infinity. So all real numbers are what the x values on this function are. Now I need to turn off my x brain and turn on my y brain. What are all the y values that live on this function? Well, if I scan like a robot scanning from the bottom up, the first thing I hit is this arrow, meaning that the beginning of this, if I had enough graph paper, would be at -infinity. And if I keep scanning, it does look like it tops out here, but take a look at the whole function. It actually doesn't top out. It actually keeps going all the way up in this direction. So this guy keeps going on and on and on in that direction, which it's a +infinity at the top of that range for the y scan. For C, again, I apologize. Let's pretend like this goes here and this goes here. For C, I'm going to do a left-right scan. Remember, scan left to right. If I scan, the first thing I hit is an arrow. So this must go off to -infinity on the left. If I continue to scan, I've got values, values, values for days, right? Values, values, values. I end on an arrow that goes off to +infinity. So all the x values on this is everything between -infinity and infinity. Turn off your x brain, turn on your y brain, scan bottom to top. If I scan, the first thing I hit from a y perspective is -3. The last thing I hit from a y perspective is +1, 2, 3, 4, 5. So the only y values that live on this function are everything between -3 and 5. We don't have any y values below here and no y values above here. Go ahead and try D, E, and F from a domain and range perspective. Pause the video and then check your answers. Okay, go ahead and check your answers here. And again, I made these things go to the whole number so we weren't dealing with estimating decimals. But go ahead and check your answers. Make sure that you have hard brackets on these -4 and the 4 and the -6 and the 5. They go all the way up to and include those 5. If you want to know what it would look like with a soft bracket, if you ever saw a line that had a big open hole and then going off like this would have a beginning of a soft bracket on these x and y values. Okay, so this would indicate a soft bracket. This nice solid dot there, or the solid line all the way through here, that's when we're saying it includes the numbers. Okay. So let's flip to a discussion you probably had in Algebra 1, the vertical line test. If you remember, the vertical line test helps us tell if it's a function or not. If you can imagine any vertical line, if any vertical line that you imagine hits or cuts through the graph more than once, not a function. Okay? I think you probably remember that from Algebra 1. Whenever you looked at these functions and you pictured vertical lines cutting through these things, if at any point you came up with a vertical line that would cut the graph or hit the graph more than once, you declared it not a function. Okay? So if we take a look at graph A, B, and C on the previous page here, A, B, and C, think about all the vertical lines in the world and what they could possibly look like. This vertical line, oops, that wasn't a vertical line. This vertical line obviously doesn't hit anything, but if you scoot closer to here, you could picture a lot of different vertical lines that would cut this circle more than once. So A fails the vertical line test, not a function. So no, not a function. If on a quiz or test you would like to use that as your justification, instead of saying this X value has more than one output Y value, if you would prefer to say fails the vertical line test, we would take that as a justification as well. Let's look at graph B. If we picture all the vertical lines in the world, we can't think of any vertical line that cuts this graph more than once. So B passes the vertical line test, and yes, it is a function. Graph C, we're fine here, fine here, fine here, fine here, but as soon as we get here, we're touching this graph all these places. So this fails the vertical line test at this point here. So that is not a function for C. If you look at D, can't find anywhere, we're a vertical line, so we pass, yes, we're a function. Same thing for E, yes, we're a function. Same thing for F, yes, we're a function. If any of that went too fast, go ahead and pause the video and take a look at these and see if you can prove to yourself that those graphs pass the vertical line test. The last two concepts we're going to discuss today are characteristics of functions that you probably have not discussed before. So let's look first at increasing and decreasing intervals. At its heart, increasing and decreasing is not a difficult concept. When you look at this graph on the right-hand side, it's fairly simple to see that this graph is increasing here, and increasing here, and decreasing here. That's not a difficult concept to agree with. Increasing, if we want to put it in math terms, is defined by saying as x increases, y also increases. Okay? So that's the mathematical definition of what you see with your eyes here. In plain English, as you look at the graph, left to right, the graph goes uphill. Always read this left to right. On the other hand, for decreasing, in math terms, as x increases, y decreases. That's the math way of seeing what you see with your eyes, of saying what you see with your eyes here. As the x values go right, as they go positive, the y values go down, they decrease. In plain English, when you look at this, from left to right, the graph goes downhill. Not a difficult concept to understand with our eyes. The hard part comes in when you need to describe to me when this is happening. Over what intervals is this graph increasing? Let's first take a look at this first interval here. Clearly we can see during this window of time this graph is increasing. You will talk to me about increasing intervals in terms of x values. You will tell me that this graph is increasing in the window between -5 and -2. This is the window. -5 to -2 is the interval or the window during which this graph is increasing. It increases again in the window between 1 and 3. It increases again between 1 and 3. X values. X values to declare your increasing interval. Do not tell me why. Do not tell me y values. A lot of students often say, oh, it's increasing from -3 to 1. I don't want to hear y values. I want to hear x values. When you say the word increasing, I've already got a picture in my mind that the y values are going up. I've already got that understanding. What I need you to tell me is when, in what window of x values is that going up. Use x values only. Similarly, for decreasing, you're going to tell me the interval or the window between which it is decreasing, the x values during which the graph is going down. So you're going to tell me between 3 and 5, this graph is going down or decreasing. Okay. Again, it's a simple concept, but declaring it in the intervals gets a little mixed up in our heads because we're so used to talking about things in y terms. I would star this page or highlight this page, come back to it as often as you need to. This is a foundational concept that you'll be using for the rest of the year. Another foundational concept is end behavior. Again, a very simple thing to look at visually, but when you try to communicate it in math terms, sometimes it gets a little backwards. So what end behavior is basically the appearance of a graph if you follow it to its ends. If you follow it all the way to the left or follow it all the way to the right, what happens? First, look left. As the x values approach negative infinity, as we go forever to the left, what is happening to the y values? As x goes to negative infinity, y goes to, notice the y values will go up to positive infinity. On the right-hand side, as x goes to positive infinity, as we go right, as we follow this thing all the way to the right, as x approaches positive infinity, y goes to positive infinity as well. This first part of the phrase will always be the same on the left, and this part of the phrase will always be the same on the right. We hardly ever type it for you. We did in the notes today, but you will need to come up with this on your own to tell me on the left-hand side, as x goes to negative infinity. There's no math to be done there. That's just declaring that you're talking about the left. This is where the math happens. This is where the assessment of the graph happens. On the left, as x goes to negative infinity, you tell me y goes to positive infinity. And then same thing on the right. This is always the same on the right-hand side. X is always approaching infinity on the right. What's happening on the right when the y values go to infinity? I'm going to work through this first example here, and then I want you to try 2 and 3 on your own and then check your answers. So let's look at domain of number 1. We're going to declare these in interval notation, of course. The domain of this, on the left to the right, scan like a robot, left to right. The first thing I encounter on the left is an arrow, which must mean I don't have enough graph paper to reach negative infinity. On the right-hand side, I go all the way to positive infinity. That's the last thing I encounter on the graph, positive infinity. Now turn your X brain off and turn your Y brain on and scan this like a robot, bottom to top. What's the first thing I encounter on this graph from the bottom? This value here of positive 3. What's the last value I encounter as I follow this graph up to the tops of it? I encounter arrows, which must mean I don't have enough graph paper to show me that it goes all the way to infinity. Turn your Y brain off, turn your X brain back on because we need to talk about increasing intervals in terms of X values. What window of time is this graph increasing? Hopefully you can clearly see that this is the portion of the graph that is going uphill. We just need to tell somebody over the phone or with this interval notation when, over what values is this increasing. Well, it starts increasing at 1. It stops increasing, well, it doesn't. It goes to infinity. This increasing interval uses soft brackets. You will use soft brackets for increasing and decreasing all the time. There are no hard brackets for increasing and decreasing. If you'd like to know why, you'll learn that in calculus, or you can ask your teacher as a sidebar. We're not going to get into it now, but increasing and decreasing always have soft brackets. So if the interval of increasing time is between 1 and infinity, hopefully you also see that this part of the graph, as you read it left to right, is going downhill. The beginning of that decreasing interval is over here. It starts with a negative infinity. The end of that decreasing interval is this value of positive 1. So the decreasing interval, the interval over which this graph is decreasing, is from negative infinity to 1. For end behavior, we were nice and we typed this for you here, this beginning here for you. Usually we don't type that for you. You have to come up with that on your own. So on the left-hand side, on the left-hand side, as x goes to negative infinity, if we were to follow this graph forever in this direction, the y values would be increasing up to positive infinity. On the right-hand side, the right-hand end, as x goes to positive infinity, if you followed this forever to the right, once again, the y values will go up to positive infinity. And again, we type this for you. We rarely do this. You're going to need to come up with as x goes to negative infinity, y goes to positive infinity, and so on. Go ahead and pause the video, attempt questions 2 and 3, and then check your answers against what I'm about to put up here. Okay, go ahead and check your answers. If at any point you're taking a look at this and comparing it to your graph and you don't see why you got something wrong, please check with your teacher. All right, thanks for watching. Go ahead and try your homework for the day.